Okay, let's stay here. I'm working with Thiago. I'm from Rio de Janeiro, from UF, Universidade Federal Fluminense, and I'm working with Thiago since I was skinny. So we work for a long, long time, and we study a lot of things. And doesn't matter. So the title of my work is Quantum to Classical. So that don't care with the title. When it's necessary, that's the title. So we're gonna try to find counterintuitive phenomena in quantum engines. So, here, okay, let's go. So first let's build everything. So let me back. So guys, just stones and sticks, no big guns, no equations, just sketches. So don't worry about it. Will be really, really nice. So first of all, I'm gonna tell about thermodynamics. So everybody knows about Carnot and everything else, and the studying of heat engines, and until Gibbs. So wow, we have the modern thermodynamics. So what is quantum thermodynamics? So we have this basis. They build everything for us, and with quantum mechanics, with powers, we are trying to follow and find the quantum revolution. One example of that is the maser, and after that, so they found the laser. So they found a theory and the machine. So we are doing the opposite side. We don't have a machine, but we have the theory. So I love that, so let's go. So everybody remember that for a classical engine from school, and so that doesn't work for us because this phenomenology don't work here. So we're gonna find this study, the magnetic quantum auto cycle. So we just have to care about populations and energy levels. So, and auto cycle is awesome to study because he only works during these adiabatic strokes and only change the heat during these achoric strokes. So everything is more easy with auto cycles. So we have that. So we have the classical here. He works like that. So the difference between the classical with pistons and gas and volume to the quantum with populations and energy and magnetic auto cycle is the entropy changed to the other side, to the other counterclock-like. So that's normal, counterclock-like in a diagram entropy by electromagnetic field. So that is what we have. So we love when that happens. So what we're trying to find, this counterintuitive phenomena. So what we do, we have the same system, the same auto cycle, but we change the baths. The system stays the same, but we change the hot bath with the cold bath. So the cold is still hotter, and the cold is still hotter, and the hot is still colder. Get colder. So we have that. So with changing the temperatures, what we will get is that. They are both quantum engines. That is the normal counterclock, and the counterintuitive rotation, it's clockwise. So the difference here is just the temperatures of the bath. So I got the compression, and now I code the system, and my entropies get down, and expansion, I got work. So, and I have to hit my system to become and close the cycle, and let's go. That's it. So that is the only equation of this presentation. So it's a really, really simple. So two particles spin half, and let's see what they found. Thiago, my advisor, and Daniel, his friend, they work on it, and they show. They saw this bidirectional rotation, efficiency gain, mode change, a lot of counterintuitive phenomena. And my work is grab the sticks and stones and find what I get. So To do that, I take out this quantum adiabatic process. My system now doesn't go out of equilibrium. I know everything. I'm using classical thermodynamics to do my system now. My system, I have a quantum system with a classical Otto cycle. So I have the same system with classical process. Yes, that. And wow, we still find the same counterintuitive phenomena. So quantum adiabatics, so doesn't care. And that is my mode change regions. Here we have engines and accelerator and blah, blah, blah. Comparing with the quantum case, it's terrible there, but they are different. We can see, actually, without coupling, they are the same. Because I only have two particles, they don't interact, so I have the same case for quantum or for classical cycle. But when I increase my coupling, I have two different things. I have the same problem, but I'm looking for different ways. So, okay, so they are different. But I still found the same classical, I still found the same counterintuitive phenomena. And I have to, just to show here, look this little island here. In this little island, all the temperature of the cold bath is hotter than the hot bath. So that is a graphic temperature for temperature. So look here, look here. So here, all the temperatures, cold, are hotter than the hot. So here, my system always will have this counterintuitive phenomena. And we still found that. And we still found the efficiency gain. And we still find efficiency gain, and everything else the same as they found. And so with the classical case, we decide to look for the magnetization. So what happens with the magnetization of the problem? Because we have the system in equilibrium all the time. We know everything about the system every time, during the entire cycle. So the first thing we can see here, the quantum case, the quantum system with quantum process, it is totally restrained in the classical engine. The same behavior of the magnetization, but the entropy, okay, he's normal, he's not normal. But the magnetization is still with the same behavior here and here. But in the classical case, we have a problem here. Magnetization do a lot of crazy things. And looking at that, because we know everything about the cycle, everything about the system, and what's happened. And I don't know if it's better, it's good for looking, but we have a lot of different behaviors for the magnetization. So we have increase of the magnetization of temperature. So, and that doesn't look like a phase transition. We are looking at that with calm and okay, let's see what's happening. We have time to do that. And conclusions, okay. The work is just that. So we still find this counterintuitive phenomena in this quantum system operating through classical process, and the quantum cases is totally restrained in the classical cases over the magnetization conditions. And what's next? Obviously, we have these problems of it's totally simple, and we want to extend that for more bodies, and try to see that with photo cycles, and specifically look for this large S, for the largest speed limits. So we have to find here, with the S large, the classical case. So let's read the Patria and see if that's right. So thank you, guys. And I have to say thank you for they pay my bills, and I'm here because of that. So thank you.
Thank you, João. Questions?
It's actually a curiosity.
What?
It's actually a curiosity.
Okay.
You told that you are doing this mapping between classical and quantum, and this is all numerics, right? So are you translating the quantum objects to the semi-classical or classical version, or are you doing the otherwise, like...
Look here. We have this Hamiltonian. We got their, the simple way to look that, we got their eigenvalues and uses the partition function and build the entire thermodynamics, entire thermodynamics with that. So I got, and I evolved.
Classical definitions of entropy.
Yeah, I have the Gibbs, everything. So I evolve my system, fixing my entropy, change my external parameter, my magnetic field, but and I got my temperature of the system. I do that completely with Python. So I don't want to talk about code, but my system is evolving quasi-statically. So it's classical, but the system is quantum.
Cool.
Okay?
Thank you for the very interesting talk. Are you guys thinking of a specific experimental platform to realize these auto cycles?
I think about it all the time. Actually, when I was in Paraty, I saw Thiago, look that, if I change the coupling, oh, that can be a sensor. And he's, what, from measure what? Oh, pressure. Because when I have pressure my system, the coupling change, and okay, we have different methods for measure the pressure. Okay, so what we are thinking is, has a optical case for the auto cycle. We are thinking about it, and to do that in UFI because we have a stronger group of optical, quantum, and blah, blah. Actually, we are the same group. So reproduce that there. They have entire apparatus for quantums and classical and
so
blah,
you're
blah.
thinking of applying it to like Bose-Einstein condensates, optical lattices, these kinds of systems with like cold atoms,
Yeah.
essentially.
The UFI, a professor there has an auto cycle with light. So we are planning to join with, oh, let's do that together, see what we can find, let's go.
With light, so like the
Yeah, with
photons
light,
are
with light.
the
Yeah,
fluid.
yeah.
Oh, that's very cool.
Yeah. No, not spin halves. We have to build everything. We have to change everything. First, has a counterintuitive phenomena. No, so let's go. So thank you, Victoria.
Any more question? So thank you, João, once again.
Thank you, guys. See you around.
So our next speaker is Marco Antônio Manya Suni.
Hola. Hello. Good afternoon, everyone. Today, I'm talking about two areas, interesting areas, that is discrete time crystal with quantum sense. Hola. Hello. Oh, okay. Sorry. So. Okay, the main idea to this project investigation is that connect, propose some quantum sensors to detect weak fields. The idea is connect with experimental results, and the first instance we are working theoretically and we actually we are discussing the experimental implementation. Okay, so that is this is my point. So what is my motivation? The motivation here is that this paper, the PRL, that is when the guys studied the robustness of the discrete time crystals in presence of disorders. Okay, so in this case, for example, in this paper. Okay, I don't know how it's working this one. Okay, in this case, this article studied the results, experimental results of these molecules, of the bad molecules, and he in this part put the measurement results. Okay, so the for the A molecule in this case corresponds this E experimental results. Okay, so for the B molecules is the D option. So this behavior that's going down after certain time is a characteristic of the time crystal. Okay, so after if as we are interested connect with experimentalists, we need to take some models. What model can be implemented experimentally? So for this, there is this paper exploring the different geometries to implement experimentally, and propose these options, the linear chains, spin systems, and polygonal geometry, and this is a star geometry. Okay, so okay. What is our model? In this case, we take the simplest model, that is a star-shaped model, that is this part. Is interacting with AC external field. And what is the point here? The point is the AC HC field is that weak. It's very weak. And in the Hamiltonian, the systems, in this case, is described by this Hamiltonian, and in which the first term is interacting only in the central spins with surrounding spins. That is uniformly interacting, okay, via Ising interaction. And the second part, we consider local disorders, for example, this, and in the X and Z directions. And the third one, in this part, the third one is this part is the H AC field that is we are interested in, okay? So after this is the kick term that is to give the system the periodicity, okay? And yeah, that is all. After we need to make how is the system in presence of disorder of external field, for example. So for that, we need to study quantum Fisher informations and methods of moment. Okay, here's the part where is the theoretical descriptions. Our Hamiltonian is periodic Hamiltonian that satisfies the relations. And okay, satisfies the relations, and the Hamiltonian in different times does not commute. Okay, so in this case, our system, in principle, the system's evolution is described by the evolution time unitary evolution operator. Okay, so this operator due to does not commute the Hamiltonian, it's difficult to solve analytically. Okay, so we discrete the times small steps. Okay, so in this case, the quantum state is described by this one, and here I show the quantum Fisher equations and the method of moments. Okay, the quantum Fisher informations in this case is for pure states, so take this form. Okay, if we have different. Generally, the general expression of quantum Fisher information is a matrix expression, but in this case, it's simply case. Okay. The method of moments is another amount that we are interested. That is described by the change of the expectation value with respect to AC field. Okay, so the method of moments has is important to consider one observable, optimal observable. Okay, the optimal observable depends also of the initial state. What initial state you need to prepare the experimental implementation. Okay, so in this case, if we consider the magnetization as best observable, we need to take the initial state highly entangled state. Okay, if we take the parity operator as optimal observable, we need to take the initial state coherent spin state. Yes. So the results in this case showing the quantum Fisher information that is a solid line for different size of the systems. And okay, in this case, in the first times, NE2 is trivial case, it's 2 spins. So after we have NE4 and NE6, and the quantum Fisher informations with the times, with the periodic times, increase. Okay, in this part, increase quadratically after is saturate and try to maintain constant after increase again. So in the after certain time, this one going down because the system lost the coherence behavior in this case, and going down, your system is not more sensitive. Okay, sorry. This one? Here. No, it's divided. It's divided by t squared. Any n pi and t squared. Okay. Yeah. So this one. So in this case, I'm showing the dependence of the best observable to method of moments, and okay, here we have the dashed line is for method of moments that tell us that okay, the quantum Fisher information give us the system is more sensitive to change of the field HC. Okay, so the method of moments located how many periods you need to apply to get the measurements with high precision. Okay, so this is the point in this case. This part, the 10 power 2 close. Okay, and that's the point. In the right side is showing that SEC in this case the magnetization is not good observable for this initial state. Okay. Here's only a considered disorder where we observe the robustness of the crystal time. Okay, so here we show the same behavior that before or previous slide, and that's all here. Okay, now I am interested in analysis. thank you. We are trying to understand why the method of moment has located the time when we do the measure with high precision. Okay, so in this case, in this picture, I plotting the method of moment with respect to AC field. So here we can, and it is horizontally, okay? Vertical axis for different times. That means we have a maximum point, and another times here, for example. Sorry. Okay, the underline 227 is the position of the maximum point, method moment. But the another times is before that time, okay? So after this value of the HC is going down, that means the system is not, we cannot to do the measurements with good precision, okay? And here the derivative of the expectation value of this observable give this is the K value to give the behavior of the maximum to find the method of moments, okay? Here I choose the initial state, GHZ. In this case, the quantum Fisher informations start from the maximum value, okay? That means initially the quantum system is highly sensitive to presence of the field, okay? So, okay, so in this part, okay, the same way where the derivative of the expectation value say for us that this is the K term for the method of moments has this maximum in certain time, okay? And that is all. And the expectation value is normally, in this case, is the magnetizations, is the characteristic behavior also. This one that is going line, showing the coherence, the behavior of the systems, and after going down. Summary. In this case, I did summary because that is I have not yet the experimental implementations we are discussing right now. So the summary is quantum Fisher information depending on the size of the system, because if we consider more spins, the system is more sensitive, and the time crystal is increasing the time, okay? So it's independent of the observable, yes, because we have not any measure of observables in quantum Fisher information. But the method of moments, yes, in this case, inherently depends on the observable that is chosen to be measured, yes. Because if we work with the coherent spin state, we cannot use the magnetization as best observable, okay? If we use the GHZ state, the optimal observable is the magnetization, yes? I think that is all, and thank you so much.
We have time for a very quick question. Somebody?
Thank you for the talk. people normally use quantum vision information for parameter estimation, something like that. Can you say something about that in your results? Because I didn't listen in very well.
Here, yes, the quantum vision information in the bibliography, you can find the variance of some observable, all right? So in this case, we are describing like derivative of the quantum state and to describe the sensitivity of the quantum systems. And we are using method of moments to estimate the parameter that I know. That is, in this case, the method of moments is working to estimate the parameter. That is, the uncertainty of the parameter that we are interested is same to inverse of the method of moments in this case. Yes, we can. In this case, we can do that. For example, if we measure the magnetizations here, and we have the HT, okay? HT, in some point, we have the measurements. I don't know, in this case, I put something like this. Our results is going down, something like this. And if I use in this HT value, and the method of moments, okay, the variance, for example, in the H, the uncertainty of the HAC here is a squared method of moments in this case. This is the uncertainty, and I can locate it in this case, something like this. This is the uncertainty on the delta, the H. And if the people, if we measure the magnetization, for example, for this H, we can find it with good precisions into this uncertainty, this interval.
Thank you again, Marco. So we now go for our last presentation in the section. So our next speaker is Federico Garcia. Thank you, Federico. It went. Yeah, it worked. So here's the line, one thing. Just to pass, you see it going.
But I don't think it works.
No, because you have
yeah,
put here.
but it doesn't matter. I can
Yes,
just
no problem.
yeah,
If you
sure.
want, we can put there.
No. It's
Perfect.
okay.
So it's
Okay. Thank you. Thank you for staying till the last moment. I'll try to be as brief as possible. So I'm mainly going to talk about my results that were recently posted on this archive. It was mostly a study of what happens to entanglement in a quantum spin liquid once you make it interact with a non-controlled bath. So let's first start by reviewing what a quantum spin liquid is. It's a quantum phase of matter where quantum fluctuations are so big that you don't get any order, even down to zero temperature. And it was initially formulated by Anderson. He was studying high TC superconductivity. He was thinking of an antiferromagnetic lattice defined on a triangular lattice. So you can see that because of this geometry constraint, there's a frustration that impedes the formation of an antiferromagnetic order. So you can think you can classically put an upspin in one side, then a downspin, but then the third side is not clearly defined. And this led Anderson to think that the ground state of this Hamiltonian was actually a massive superposition of different singlet configuration in what is called as a resonance valence bond. And these kind of states have very desired properties. For instance, their excitations have anionic properties, meaning that if one excitation, let's say B, surrounds another excitation A, it acquires a non-trivial phase. And importantly, the property that I want to discuss is that these phases have long-range entanglement, meaning that the ground state, if you take the ground state and you split your system between two regions, A and B, and then you compute the von Neumann entropy, then typically you would expect some area law scaling. So the von Neumann entropy would scale as the length of the perimeter of this area. But now you get this additional gamma contribution, which is a universal parameter for a topological phase. It turns out that actually the ground state of a triangular antiferromagnetic lattice, its order, it's a 120 antiferromagnetic ground state. But if you play with the next nearest neighbor antiferromagnetic coupling, you actually get a quantum spin liquid in theory. And there's very recent experiments from Oakridge National Lab where they have shown that it is likely that ytterbium Delaphosite material are actually hosting this phase. And like that, many other candidate materials have been proposed for other quantum spin liquid models. In particular, I'd like to focus on ruthenium chloride, which is a candidate material for a Kitaev spin liquid, which is a spin liquid defined on a honeycomb lattice. And in this case, the frustration comes from very anisotropic Ising-like interaction, where for one distance you have Ising-like along X, for the other along Y, and for the remaining one along C. And despite being a many-body problem, it can be exactly solved due to the macroscopic number of symmetries. So for each hexagon, you can define that quantity W, which is called the Wilson operator, and it's a symmetry of the system. And this has led to a following understanding of the model. So you have two kinds of excitations, which are fractionalized. So one is associated with precisely this Wilson operator, and it's called static bisons. And the other excitations are called itinerant Majorana fermions, and its order parameter is just the spin-spin correlation function. This is very attractive because you could get topologically protected qubit. So you could get a platform where topology protects your bits of information. And this was very recently realized in cold atom setup by Lutkin's group. But now going back to the actual candidate material, this has been extensively studied. For instance, here I'm showing neutron scattering data. There's also thermal transport and Raman scattering data, but still it's not clear whether this material is actually a quantum spin liquid, which leads to a natural question of whether these states are actually stable if they interact with a non-controlled system, path. So again, I'm just gonna discuss a bit more about what is the dissipation and what is unavoidable. So, oops. Sorry. So whenever you have a system, here I'm plotting a superconducting qubit, you have some degrees of freedom over which you don't have control. For instance, you have phonons, impurities, electromagnetic radiation, and this led your system to lose information, energy, exchange particles, and in general, it's a complicated dynamics. So for instance, even the blue window, which is kind of the easy dynamics, you just get an exponential relaxation to some steady state value. But you can get deviations from that, and these are essentially controlled by the spectral properties of your function. So if you make your bath to acquire content in the near zero or to have sharp features, you actually deviate from an exponential relaxation and go into this non-Markovian regime, which is harder to cover. So even the Markovian regime is very complicated to model. You typically are just restricted to, let's say, or the order of 10 qubits. And going to the non-Markovian regime, it's even harder, as Felipe already mentioned, and there's just very few methods that can handle this. But nevertheless, taking into account dissipation is very important, and it's not only detrimental, it can also be fostered for useful things. So for instance, by manipulating the spectral properties of your bat, you can actually make your system go into a desired state. And this is actually called dissipative engineering, and it's useful. And it's also conceptually useful because it can explain how classicality emerged. So for instance, here I'm showing some results we obtained last year, where we started from quantum many-body dynamics, which are complicated. And when we include the proper dissipation, we can transition into some classical dynamics, which are more easier to model. So dissipation can also explain how classicality emerged. Now, merging these two topics, there have been few approaches before to discuss what happens to a spin liquid when you couple to an uncontrolled bat, but most of the studies have typically just restricted to what happened to the spectrum and not what happened to the entanglement. And they require very symmetric modeling of the dissipation, which allows for exact solvability. But they have not discussed what happens to entanglement, and this is because quantifying entanglement at finite temperature is something difficult. So here I'm showing this gamma correction, which is the long entanglement correction, and this has a very well-defined formula at 0 temperature, and it's known as the Kitaev-Preskill prescription. So you have to take a bunch of partitions and compute the von Neumann entropy for such partitions. But when you go into finite temperature, this quantity cannot be used. So here I'm showing results by Grover, where he shows that when you use this gamma parameter as a function of temperature, you could actually observe that for a range of temperature, this quantity indicates that your system is actually in a long range order, long entanglement range order. But when you consider the proper definition of entanglement at finite temperature, you observe that this quantity is actually a false footprint. So our approach was to focus on multipartite negativity, which means that we do not take into consideration a particular partition, but take into consideration any possible bipartition. And there's a very recent study on quantum spin liquid, which have shown that as frustration increases, the entanglement formation only lies into closed loop shapes. Meaning that for open shapes, you can always find a bipartition which is not entangled. So our approach was to take a microscopic modeling of a quantum spin liquid and a realistic dissipation. So we take our Kitaev model and couple it to a bosonic bat, which induces energy loss and decoherence. And we consider two cases. One we call local coupling, where we couple each local spin to an independent bath. And then another one called global, where we couple the whole system to a unique bath. And this is modern. These two regimes can be varied, whether you're considering a optical lattice by changing the distance between your atoms, or in a real material by changing the phonon coherence length, for instance. And we perform real-time simulation using several methods. Here I'm showing the 3 methods that we use. They all have advantages and pitfalls, but the thing that I want to highlight is that one is appropriate for Markovian simulation, and the other 2 are appropriate for non-Markovian simulation. So first I'm going to show the result for weak coupling, so Markovian. And what we observe is, let's just recall that as before, frustration allows entanglement formation in a quantum spin liquid only in closed loop shape. But when we study the open quantum system dynamics, we observe that for a open shape, we observe some transient where this is non-zero, but it eventually goes to zero, in analogy to the previous result at zero temperature. Now, this is interesting from the theoretical point of view, but it's not easy to compute experimentally. So we also compute quantum fission information as a quantum entanglement witness, which is an accessible quantity, and it can be computed either by neutron scattering data or by time resolved in elastic X-ray spectroscopy. We also observe how the excitations evolve, and we observe that they decay in different time scales, and the Bison order is always lost. And now going to the more challenging non-Markovian regime, I'm showing exactly the same data, and it's more interesting in this regime because the steady state can be non-Gibbsian, and what we observe is that, for instance, the entanglement formation in closed areas, which was forbidden before, it eventually died. In the non-Markovian regime, it can actually stabilize to a non-zero value. The other thing that we can observe is that as the steady state is non-Gibbsian, observe that, for instance, the flux order is not lost for a temperature of 0.5, whereas in the weak coupling regime, we observed that it was always lost. So you can engineer the steady state by changing the spectral properties of your function. Here I'm showing the same the steady state result for the final method. We observed that for the local coupling regime, the state is just a kita F Hamiltonian, meaning that it's resilient. But when we include global interactions, the BAT induces new interactions of a Heisenberg type, and as we tune in the strength between the BAT and the coupling, we can actually drive a quantum phase transition between a quantum spin liquid and a quantum ferromagnetic phase as these BAT-mediated interactions become more important. So in conclusion, I've shown how by tuning the BAT properties, you can actually change the anatomy of the entanglement in a quantum spin liquid, and you can also drive it to a different phases, for instance, a ferromagnetic phase. Here is the QR code for our group website publication where we post all other publications. Thank you.
Questions?
Thank you for this very nice talk. Stupid question, why they call this excitation bisons?
Why they call it bisons?
Yeah.
It's basically because they define a gauge theory. So these, let's say the itinerant Majorana fermions are just propagating in a background of fixed bison values. So these can take values of plus or minus 1. So these are just gauge interactions that can be turned on and off.
Okay. Thank you.
Any more questions? So let's thank again Federico. So this was the last presentation. I would like to thank everyone for being here and especially for the presenters. All the works are very interesting. So thank you very much for all, and we see each other tomorrow.